Here we are given the fourth degree polynomial 3x to the fourth minus 13x cubed minus 23x squared plus 117x minus 36, and asked to find the rational zeros using the rational zero theorem and a graphing calculator. From the rational zeros theorem, we know that the candidates for the zeros will all have numerators that are divisors of negative 36, the constant term, and denominators that are divisors of 3, which is the leading coefficient. So they will be in the form P over Q where the candidates for the Q are just 3 and 1, plus or minus. But the candidates for the numerator are 1, 2, 3, 4, 6, 9, 12, 18, and 36 itself. So if I start to list these, starting with the denominator 3, I'll get plus or minus 1/3, 2/3, 3/3, which is 1, 4/3, 6/3, which is 2, 9/3, which is 3, 12/3, which is 4, 18/3, which is 6, and 36/3, which is 12. That's all using the denominator 3. Now, I'm not going to reuse any of the candidates, so I've already used 1, 2, 3, 4, 6, and 12. We should add 9, 18, and 36. So at this point, we know that our rational zeros are all between plus or minus negative 36. I will use that as the x-min and the x-max when we're drawing this graph. So first of all, I have entered the function in the y equals screen. Now we're going to go into the window and enter negative 36 and 36. And we can leave the negative 10 and 10 for the y-min and y-max, because what we're interested in at this point is just where the curve crosses the y-axis. So let's press graph and see what we see. Oh, that's hard to tell what we're looking at here, where we can certainly come much closer to the y-axis. As a matter of fact, I think we can at least come to the negative 9 to 9 for y-min and y-max. I'm going to actually come all the way to negative 6 and 6. And I don't think we're going to have lost any of those zeros. We see 4 places where the curve is crossing the x-axis. And we're not going to say that we know what they are exactly. We're going to say they are approximately, I'd say, plus or minus 3, positive 4, and something that's a little bit bigger than 0. Very, very close to 0. So I'm going to do an educated guess. I'm going to at least check to see if it's 1/3. So I think the ones that deserve further examination, at least in the beginning, look to be -3, 1/3, 3, and 4. Now, we don't know that those are the exact zeros, but there are zeros close to those numbers. We can use synthetic division to verify that these are the correct numbers. If I use -3 as a divisor and copy down the coefficients so that I can do the synthetic division, I'll have 3, -13, -23, 117, and -36. 3 will be the leading coefficient in the quotient. 3 times -3 would be -9. Add -13 would be -22. -22 times -3 is 66. Add -23 is 43. 43 times -3 is -129. When we add positive 117, we get -12. -12 times -3 is positive 36. And we see that we do get 0 as the remainder. So the actual rational zeros, as we form a list, -3 will be one of those. Now let's try 3. I'm avoiding 1/3 because it's a little messier. I'll come back to it. So 3 will be the leading coefficient in the quotient. 3 times 3 is 9. 9 plus -12 is -13. 3 times -13 is -39. 43 plus -39 is 4. 4 times 3 is 12. -12 plus 12 is 0. So we can add 3 to the actual zeros. Now let's try 4. Three will continue to be the leading coefficient in the quotient, in the next quotient. 3 times 4 is 12. -13 plus 12 is -1. -1 times 4 is -4. And we get remainder 0. This last quotient is degree 1. It represents 3x minus 1. Since the -1 is the x to the 0 term, and 3 is the coefficient of x to the first. So our last linear factor is 3x minus 1. And we know that 3x minus 1 equals 0 if and only if x equals 1/3. So we have confirmed that 4 is a rational zero because we did get a 0 as a remainder in the last division. And we've confirmed that 1/3 is an actual zero because 1/3 is a zero of 3x minus 1. So the actual zeros here were -3, 3, 4, and 1/3.